people might be going to sound over because it's about optics and telescopes, right? So you know, as like astronomers, we care about like our tools of trade, we care about how it works, and we want to know like exactly what the limitations and any protections or whatever, right? So this is mainly what the talk will be about. So, okay, this thing not working. Yeah, so just to give a brief like 3-slide summary of like what you can like take away from this talk, how does a telescope like let us see more stars, right? So in general, the first way it lets us see more stars is obviously by magnification. So let's say you want to see planets, planetary nebulae, lunar surface details, right? But most of the time, the more important factor when it comes to a telescope is the aperture, which is the diameter of the object. So there are two ways that aperture is more important than magnification in determining like how good a telescope is for like astronomical purposes. So the first thing is like, you know, basically the bigger the telescope, the sharper your images will be. And the second thing is that the bigger your aperture, the brighter the image, right? So this is a very brief summary of like what you need to know. And then the rest of the talk will really just like digging into like why is this the case. So it's very fun, or perhaps not, depending on which side is slant. Maybe it was like, you guys have heard of this like super common idea that like a telescope is just a light object, right? So you're collecting light flowing in from this like large surface area. Then you're like squeezing it into like a very like narrow like cone that comes out. So that increases the brightness of the image. And it's not an immediate picture, it does explain some things, but then oops. But obviously it's like this in this picture you're sort of thinking as like light as when you could, right? So it's something that occupies more volume space, if you squeeze it, you can manipulate it. But honestly the light isn't anything like that. So optics is really like a quite complicated subject. So here we just like briefly go into like some basic ideas in it. So as you know, like the parts of the telescope, like one right here, this is my own like personal setup. It's a Schmidt category telescope. So several parts. The first part that we really care about is this part called the optical tube assembly, or OTA, which is like the main model of the telescope with all the extra eyepieces and stuff. The second part is the mount and tripod right here, and then eyepieces and other accessories, right? So the more important parts that we care about today is the optical tube assembly and eyepiece, right? So today we focus on like these two parts, right? So firstly, I'm covering a bit of my basic optics, and then when I say basic, yeah, you just need to you heard this a lot, so really diverse, right? So you need to go back and start digging out your like secondary school physics and optics and like remember how does a ray diagram even work in the first place, right? So yeah. So moving on, some key numbers you need to care about for optical tube assembly. Honestly, there's only two numbers, right? So aperture and focal length, right? So intuitively, it's very easy to understand. Aperture like sort of corresponds to how wide this part is. Focal length, how long. So by length itself is exactly by length, right? So from this two, we can calculate what's known as aperture, which is the focal length divided by aperture, which you can think of like as like telling you how speedy that this optical system sort of like focuses the light, right? Yeah. So this is a ray diagram that sort of like summarizes what's going on. Over here is the aperture, which is sort of like the width of this light beam coming into the system. And the focal length tells you like just how far does the light beam have to travel before it reaches focus at a single point. Yeah. So how does how do you like have like image formation in the optical system, right? The most prototypical kind of like camera system is known as a pinhole camera, or camera obscura. Like have any of you heard of a pinhole camera? Right. So let's say that you have 3 dots here as your image, right? So it's a red, green, blue dot in sequence right here. A pinhole camera works because red light from this particular dot can only travel in a straight line towards this point, likewise for green light and likewise for blue light, right? So what the camera does is something that sort of like takes light rays from a specific point or like angle or direction, and then it maps it sort of like to a single point from the focal plane, right? So all light rays from there point to the image there, and no other light rays can sort of like go in and interfere. And in a sense, this is how you really get like the real image of pinhole camera. When you extend it to something that's like a lens system, it works on exactly the same principles, right? So for light from the red dot here, it will pass through this lens and you hit this point, right? So when the light from the red dot passes through the center of the lens, it doesn't get reflected. that obviously just passes through too. But when it passes through here, it goes to the same point, and here, the same point. So a camera with a lens is like the same thing as a pinhole camera. But one important benefit of having like a lens as your focusing device instead of a small hole is that you have a larger collecting area. So that means you can collect way more light coming from that specific point and map it all over here. So as you can tell, the image they collect from like a camera with a lens system is a lot brighter than compared to a pinhole camera.
For a pinhole camera, is the effect of interference sort of significant, or like?
It depends on how small your hole is, so that's sort of the trade-off here. So that's why the pinhole camera is actually the best in terms of resolution and all that.
So it's not really present in
You have to put on that fraction. Yeah, that will be a fraction. So that will reduce the contrast and carry the pinhole camera image. It's not that okay. So the difference between like what we care about in astronomy versus what we care about just now is that just now we're talking about a real image coming from points on the object, right? But in reality, in astronomy, all the things that we look in the sky are like infinitely far away, more or less, right? So that means that all the rays coming from like a single point, like let's say that direction, they're all basically a set of parallel rays just traveling towards us, right? So so basically this is how a telescope really works, you know. So you have blue light coming from this single direction, like one point in the sky, they all converge to a single point on the focal plane. While the red light sort of comes in at a like slightly different angle, which corresponds to sort of a different point in the sky, right? So they're all coming at a slightly different angle, and then it all converges to one single point on the image focal plane. So that means that in order to form an image, basically collecting light from all sorts of different angles and sort of mapping it to like this single point on the focal plane to form like sort of a view image. So this is like one thing that you sort of need to keep in mind. Right? What do we mean by images? We mean by sort of light coming from this specific direction. So this is also what's known as a virtual image. Right? So this image isn't something that's like focused on this focal plane, but rather it's like a set of light rays that come from this direction, that direction, that direction, that direction. So theoretically, you put your eyes there, you can sort of see an image infinitely. Okay, so an important property of what we call a telescope is focal length, which I mentioned just now. Right? And I say that focal length is sort of this distance from aperture towards the point where all your light rays sort of converge, like into a single point right here, right? And in this focal length directly determines how much your optical system or your telescope can sort of magnify the image. And to put a long story short, the longer your focal length, the higher the magnification, and this has a directly proportional relationship. And the reason you have this is that, let's say your focal length is short. This is the size of the image for light. So basically, it's a rotation of the point that all that's like coming from this particular direction. But let's say your optical system is sort of like longer focal length, right? I'm still talking about the same object coming in from the same angle in the sky. But because the focal length is longer, this light rays sort of like travel a lot farther before your light rays sort of converge at this point, right? So you can see the image at the focal plane is a lot larger compared to just now, where you have a shorter focal length. The image is all smaller. So this is exactly the principle of how the telescope magnify things. Or actually, this is exactly how any like magnifying glass or any kind of optical system sort of like increases the magnification of stuff.
Isn't it also magnified at the wavelength of the specific light?
Sorry?
Isn't it also magnified at the wavelength of the specific light?
Yes, that's true. And how about this? But this is sort of the idealization, right, of like we want something that's like a lens or a telescope. What does it ideally do? This is the kind of thing that ideally does, right? So it just takes light from a infinite like cell points to like map it on a single point on the image. when we talk about magnification, we're talking about linear magnification. We're talking about like how a single line doubles in length, triples in length and everything. So when we talk about area, it sounds like a square relationship. So this is basically a visual representation. Like in practice, when you look at a telescope, you try to magnify something to like a very, very like large size, right? And then you're not going to get anything clearer beyond like this like fuzzy patch. And you also notice that it's also like quite dim, right? Because of like the size, because of like all the light being like spread out over a larger area. So one interesting effect of like telescope is that because of how it sort of like takes light from a parallel like set of points and basically squeezes it to a single point of focal plane, the brightness of the image across the focal plane isn't constant at all, right? But rather there's sort of like a geometric relation coming from here. So if you have light coming in more or less straight from like source, so basically your light is coming in and more or less like as parallel to the optical system. That means that the light rays is sort of like quite wide, right? Because it can enter your optical tube at quite a large angle, in a shallow angle. So that means that this distance here is quite large, right? So that means that there's a lot of light being collected and being like squeezed into this point. But let's say your light is coming in from a very shallow angle. Then the effective aperture, like how large this hole is, that is seen is basically like flattened and like made a lot shorter. So that means the light that you are collecting and sending to this particular point is a lot less, right? So effectively, you have an image that's like super bright at the center, then sort of like gradients out towards the edge. And you can actually see this in practice, right? So when you do an image, you do imaging with like a telescope, then you realize that a lot of the times, the image at the center is sort of brighter, but it gets dimmer towards the edge, right? And most of the time, this is worsened by, let's say, you have a telescope with a shorter focal length, right? Because when your telescope has a shorter focal length, your telescope can sort of like see a larger area of the sky. So that means that you have light rays coming in from a large shallow angle, and its brightness will sort of like be sort of reduced because it's coming in at an angle towards the aperture. So it becomes a lot thinner. So when you have a shorter telescope, this effect gets worse. Then this is also worse depending on how large your camera sensor is on the focal plane. So if you have a small sensor, then you're only capturing like effectively this small part of the focal length in this part of the image. So there isn't really much of a difference in like image brightness gradient. But if your camera sensor is super big, then you can sort of like capture more of this variation in angle in the image too. Then you sort of get like what's known as a vignetting effect with your like image as you can see over here. Honestly, I just put this in because I want to complain about this setup that April gave me for like a project thing. But never mind. So that was a very basic run through of like, how the OT optics works, right? So far so good. This is the easy part. Right. Okay, are you all following so far? Or are you
confused? True.
Yes.
Yeah, here. How do we know that the two, let's say the two jet rays converge at on the same plane as the two sort of yellow rays?
That is idealization. So it doesn't always happen. But ideally, we try to commit sort of like a telescope system that does exactly this, right? So this is a platonic ideal of what telescope should be. So reality often falls short, right? So far all I've been talking about is just the optical tube assembly itself, right? And I'm talking about how it focuses light and forms a real image. Then why on earth would we need eyepieces? So the reality is that, let's say if you put something like a focal chemical plate or CCD sensor at your focal plane of the telescope, then you can actually capture an image, right? Because like light coming from all of this angle is mapped to this specific point on the sensor, right? And you know, those kind of CCD sensors, they're all made of like small, like basically detectors, right? So if I have a photon hitting this like detector, then it produces like electrical response, then it just gets recorded by the digital recorder. So literally this is how like a CCD sensor captures the image, right? But if you're gonna put something like your eye over here, the image is going to be focused like your pupil, then it sort of like spreads out all over your retina. And then in practice, what you see is something like this. Right? So this is like what happens when you focus a star out of it. You can sort of like see the concentric rings and the image and everything. So the reason for that is because your eye is exactly the same thing as like a telescope, right? So our eye similarly has a lens that also acts as sort of like your aperture. Then your lens sort of converges the light in order into a single point on this retina. So your retina is effectively the same thing when you have a set of light rays that diverge from the focal plane, your eyepiece basically turns it back into like a bunch of like parallel light rays that goes in your eye, right? So from this ray diagram, you can sort of see that your eyepiece is sort of like a reverse telescope, right? So your telescope takes parallel light rays, squeezes them into this single point. Then your eyepiece does the reverse. Light coming from a single point turns into a bunch of parallel light rays, right? So in fact, if you look through like the other side of the eyepiece, it's sort of like the eyepiece that makes sense. Just that usually the focal point is also looking here, so you kind of stick your eye in there to like try to like, or you try to stick a paper somewhere there to try to capture the image, right? So here are like some of the more important numbers for what the telescope, what the eyepiece, that they sort of describe the eyepiece, right? So the first thing is you want to know is that the eyepiece has a focal length, typically from a length of like 4 millimeters towards like 40 millimeters towards like upper end. And usually you can find it like written down here as a number at this side of the eyepiece. So for example, this one is a 32 millimeter, which is sort of on the longer side, right? So with eyepieces, the longer your focal length, the wider your field of view, right? Because it's a lower magnification. The other number they want to know about eyepiece is apparent field of view, though arguably it's not as important as the focal length, right? So your apparent field of view basically tells you that when you put your eye towards like the eyepiece over here, it tells you just how wide the image is going to look like from your perspective, right? So because when you see your vision, it's sort of like, your vision is sort of like more than 180 degrees. So when you look at the eyepiece, the angle that you can see the image is sort of like narrow to like a certain like angle, right? So typically for like the most common eyepieces, we have what we call dorsal eyepiece, which is exactly this kind of eyepiece. The angle is at 50 degrees. But obviously you can like spend money to get like super expensive eyepieces, like from Astro or whatever. Then you can go up to like the so-called like ultra wide field of view eyepieces. You have like about 110 degrees worth of like field of view. The last number that may or may not be important is the barrel size of the eyepiece. Right? So the thing is that your eyepiece has to sort of like fit into a telescope, right? So most of the time your telescope has like this hole at the back that can accommodate a certain size only, right? Depending on the type of telescope you have. So the smallest is usually 1.25 inch. There are larger eyepieces, they are known as 2-inch eyepieces. Those, of course, they are like more expensive. They are a lot heavier. You usually find them with like usually larger telescopes or observatory size telescopes. And there is an older convention that uses 0.96-inch eyepieces. So if you have those kind of vintage telescopes, then it's all out of luck, right? Because you need to get special eyepieces for this telescope.
So does the diameter affect the AFOV?
It does, but how exactly it affects is quite complicated. Yeah, so this is like the realm where we go into like designing optics with like computer programs and everything, and you see how exactly the geometry of our eyepiece affect how light passes through. So when you get there, it's like super complicated. So the thing is that eyepieces all have a different focal length, right? So let's say that you have a telescope with a specific focal length. So let's say this one has 150 millimeters for focal length. Right? Yes, a focal point at this big point, you can't change it. Your eyepiece also has a focal length. That means that you can only turn light rays coming from this particular point and turn it the parallel rays if your eyepiece is not at this correct distance away from the focal point. So that's what you need to bring an image in focus, right? So usually when you put eyepiece in, you'll be a bit too far in or too far out. Then you have something known as a focuser that sort of moves the eyepiece in and out until like your eyepiece is at the exact distance for all the light rays coming from the point to turn into a set of parallel rays. Right? So for my telescope specifically, this is the focuser over here. You don't really see it moving the eyepiece in and out because this one is the mirror instead. So you have like a lot of like interesting different designs. But usually with those now like long refractor telescope, you literally see this thing mounted on the edge of the tube that moves in and out as it turns on. So this is exactly what is doing right here.
So this changes the focal length.
No, it doesn't change the focal length, right? So because you said you have an optical telescope, your telescope has this focal length, it's fixed. Your eyepiece has this focal length. You move it out, it's like this. You move it in, it's like this. Neither of it will be in focus. So when you move it exactly to this point, where this point is sort of like your eyepiece focal length, then your image will be in focus. Otherwise, the whole thing will like be blurry and stuff. So effectively, this means that every time you change the eyepiece to a different focal length, you need to like readjust the focus. So what you're effectively doing is just sort of like moving it so that lens element is sort of at the correct distance from the focal plane. So this is like what we need. Oh yeah, so I have a picture of like a refractor, so you can really see like how the focuses sort of like really literally move the eyepiece back and forth. Like. So your eyepiece is sort of like mounted at the end of this diagonal over here, and this knot basically just like brings this tube in or out and adjusts the distance accordingly. So in order to calculate magnification, you sort of have a simple formula that's very useful to memorize. Right? So maybe you all don't like doing math, whatever, right? In practice, when you want to go out and like start observing using telescopes, this is like the simple math that you need to remember. So your magnification is given by the focal length of telescope divided by eyepiece focal length. So for example, my telescope right here, it just says, I don't know if you can see it says on the ring right here that the focal length is 1250 millimeters. And then the magnification of this eyepiece is 32 millimeters over here. So this one you need to do like 1250 divided by 32. Simplify 1200 divided by 13. Then that's around 40 times. Right. So 40 times is sort of like on the lower end of the magnification limit. Right? So the telescope can go all the way from like, let's say 20 times all the way to like 200 times and all that. Your TQ is 1000 times. You can push it to 1000 times, but whether there's a point in doing that, you guys all that's all right then, right? Yeah.
So the observation changes the focal length of the telescope.
So naturally, when you have a bigger telescope, you are going to have a far longer focal length. Yeah, that's a natural thing. So when you have a big telescope, it's kind of difficult to have a sort of like wide field of view as well. So a bit more about how on earth does an eyepiece magnify things, right? So you know a telescope magnifies things because its focal length is long, but the magnification we're talking about is how big your image is on a focal plane. But when it comes to eyepiece, we're not talking about the image in the focal plane, right? We're talking about how big the image looks to you when you look at the eyepiece. So the idea of magnification here is like slightly different. So first and foremost, when we look at the image on a focal plane, all your light rays are coming from various directions. It's sort of like that bent lens element, right? So all your light rays sort of like cross at this point. Then you can think of your light rays sort of like diverging equally in all directions from this point, right? So this image on your focal plane is exactly the same thing as let's say you have light rays bouncing off a real object, right? So when you have light rays bouncing off a real object, each point the light rays are coming out and they are spreading out from here. So this is why an image that converges on a focal plane is also called a real image. Or the image you see, there's like a set of parallel light rays coming from this direction, it's known as a virtual image. So because it's a real image, you sort of like literally think of like our image on the focal plane as this real thing. So the way the eyepiece sort of magnifies this is like the same way of magnifying glass works, right? So if I have an eyepiece with a sort of like shorter focal length, this is sort of like the angle of like that you see like this object coming in at. But if you have an eyepiece with a longer focal length, then you can see that because this distance is larger, this angle is necessarily shallower. So effectively, when you get a higher eyepiece, when your magnification is higher, that means your focal length is longer, right? That means that when your magnification is higher, you have a shorter focal length, right? Because your light rays are coming at a steeper angle, right? So that means that the object you normally see that's at this big becomes this big in your view. However, when your eyepiece focal length is a bit longer, then that means that the light rays that you see are coming in from a shallower angle. Okay. So that means the object you see will be a lot smaller. So in effect, this is how eyepiece magnifies the image on the focal plane. Right. So based on this, you can sort of like calculate the magnification as follows, right? Which is what I said earlier, which is the focal length of the telescope divided by the focal length of eyepiece. And now you know the reason for that is because the size of your image is proportional to the focal length of your telescope. Alright? But it's also inversely proportional to the focal length of your eyepiece. So to get magnification, you sort of like divide this focal length by eyepiece focal length. Okay? So another way to sort of like intuitively understand this is that your shorter eyepiece has a shorter focal length, right? So that means that the light coming from focal length the light coming in from a focal plane is sort of like bends more at a steeper angle towards the light, towards the eye. Meanwhile, if eyepiece focal length is sort of like longer, then the bending is a lot less severe, right? Then that means that the light is coming in at a shallower angle. So this is sort of like the intuitive way to think about how does the eyepiece like magnify things. So effectively, when you put a telescope together with eyepiece, it basically does two things, right? So the first thing is that the telescope compresses how wide your light cone is, right? Because if you know that light coming in from a single point in the sky comes in as like a self-parallel wave, right? So you can imagine this like giant like cylinder of light coming in. Then your telescope sort of like compresses it into this like tiny like cylinder coming out of the eyepiece. So this is how like brightens up images. The second thing is that the telescope magnifies things by changing like the angle of a parallel incident rays. Right? So let's say you have a set of like red, green, and blue rays coming in from different points in the sky, and you see that they're coming in from this like slightly shallow angles. Your eyepiece sort of like ends up bending it all that is coming in like at a very steep angle. So effectively, your eye sees the red dot all the way at that angle, even though it's actually at that angle. Then your eyes will also sees like the blue dot being all the way in that direction, even though it's actually towards that direction. So this is how you get like magnification using like a telescope system.
One of the rays coming out supposed to be battery, even though like other rays coming out shouldn't they be battery into the telescope?
Yes.
Shouldn't they be battery to the telescope? The rays coming out.
It depends on which part, right? If the light rays are coming in with the telescope parallel to its optical axis in this direction, then it comes out from this direction, right? But if you change your angle a bit, like it comes in from this angle, then it comes out slightly at a different angle. Right. So effectively, you can see like what the telescope sees here is also a virtual image. What the eye sees here is also a virtual image. The telescope just does a conversion such that your cylinder of light is compressed, then comes in at a steeper angle. So that's how you get both brightness and magnification using the telescope. Makes sense so far? Or am I going too fast? Yo. All good? Any other questions? Yo, what else? Just in time to like return like this information. Sorry? Just in time to like come in and get like some information. Yeah. Okay, so the thing is that when you have a eyepiece, right, all your light rays will sort of like converge at this specific point, which is known as optical, right? So you might experience this if you're like using like the binoculars and the glasses, right? And you hold it at a distance, sort of like can see this like circle of light right here. Right. So the reason you have that is that the exit, because it's like the beam of light coming into a telescope is sort of like bounded by its finite, and there's like an edge to it, right? So when you come out of eyepiece, there's also like an edge to it. So you can think of this set of three rays, like this set of three rays over here, as literally telling you how wide this like set of parallel light beams is when it comes to your eye, right? So all of it is sort of like intersected at a particular point with a certain like width, and this point is also known as exit pupil. So one quite an important number that you care about is the width of this like exit pupil. Yeah, which is that. So because the exit pupil is exactly the place you really want to put in your eye to get like the most light and the largest field of view, right? So if the exit pupil is here, okay, this person is like going this way, the eye should be all the way right here. So we care about exit pupil because typically when you have a larger exit pupil, it results in like a brighter image. And like when you have a higher magnification, it results in like a smaller exit pupil and like a dimmer image, right? So one way to calculate the exit pupil is to use aperture divided by magnification, which makes sense because your aperture tells you like how wide your light beam is when it comes to the telescope. And when it exits the telescope, it exits with a certain weight, which is equal to the exit pupil. Right? So the difference between these two is given by how much a telescope sort of magnifies the image. Right? So when it magnifies the image at a sort of like astronomy articles, you see this formula being quoted often for binoculars, but it actually works perfectly well for telescopes as well. So that's an interesting stuff. Right? So for binoculars, let's say you have a common 10 times 50 binocular, which means that it's 10 times magnification with 50 millimeter aperture. Then that gives you a 5 millimeter size pupil, right? So if you compare that with the size of human pupils, it's typically from like 3 to 7 millimeters, right? So 3 millimeters or like 2 to 3 millimeters is the size of the pupil when it's in like bright lights. And theoretically, like in dark conditions, your pupils can dilate all the way to like 7 millimeters, right? So the way they design the binoculars is that the 10 by 50 is such that you have a 5 millimeter exit pupil, and this exit pupil fits exactly within your own eyelid exit pupil, right? So why do we care about this? Because if, let's say the exit pupil of your own eye is like smaller than the, okay wait, I'm thinking things out. If the pupil size of your eye is smaller than the telescope exit pupil, that means there will be light that's coming out of the telescope, but it's not entering your eye, right? So that means that the image you're actually seeing is a lot dimmer than what the telescope can actually provide. So in such a case, you really want to change to higher magnification. So when you change to higher magnification, all your light gets squeezed into like a smaller area, becomes brighter, and that means that you can see all the light the telescope is shining like this. So let me just do an example calculation of like the exit pupil size, right? So imagine you have a 70 millimeter f6 refractor with a 32 millimeter eyepiece. So basically this is as wide as it can go, right? So this is as large as exit pupil will typically go, and this will give you an exit pupil of around like 5 millimeters. So that means that in sort of like reasonably dark conditions, this is more or less what the size of a human pupil would be. And this is sort of like the kind of considerations that telescope makers do take into account when they are making telescope systems. So another part of eyepiece they want to care about is sort of like, okay, maybe it's not that important, but this is sort of like extra info. Right? So when you have an eyepiece, usually there's this rim of like sharply defined like edge over here that's also known as the tip stop. Right? So the reason you have a tip stop is because your eyepiece sort of like has either a barrel over here or sort of an internal metal like here that sort of like restricts the light coming in, and that gives you like a sort of crisp and like sharp edge to your image. A lot of people like it because of like aesthetic reasons and stuff like that. It's also a practical necessity because when you have an optical system, at some point you just need to cut off the light. So for example, okay, this ray diagram sort of like summarizes how you get a field stop, right? So your field stop is located at where the focal plane is, right? So that means that you can imagine this is where your view image should be, just like later on, right? So that means all your light rays over here are diverging equally from this point. And the size of the eyepiece lens over here sort of restricts what's the angle of light that you might enter your eyes from this angle. So from this ray diagram, sort of like can sort of do a image calculation of what the apparent field of view of the eyepiece is. Right? So your apparent field of view is sort of like your maximum the eyepiece is. Okay, for real eyepiece, the field stop is typically located like, let's say, within a barrel, right? So I don't know if you can see, but for this eyepiece, there's like sort of this like darker ring inside. It's located all the way inside. Right? So you typically think that the image might converge over here. That's not where the image actually converges for the telescope. The image actually like converges all the way at this point, near like where the eyepiece is supposed to be. Right? And the eyepiece is sort of like take this distance right here, and then turns it into a virtual image. So your real image all the while is just sort of like deciding like, into the inside view of this eyepiece. So that's like one interesting thing. Wait. Yeah. So the apparent field of view, in a way, you can sort of think of like it as being the angle between the light rays that are coming from the edge of the eyepiece, right? So this is sort of like the maximum angle that light rays can plausibly come out of the eyepiece and reach your eye, right? So your AF always just tells you like just how wide this angle really is, and this in effect also defines like how wide the image will look like in your own field of view, right? Because you can see things from this direction, and this direction, and this direction. So for exit people with like basically, when you have like, like when you have a high magnification, your image becomes like sort of like dimmer. And when you have a low magnification, your image becomes brighter. This is sort of like telling you the reason why, right? So when your eyepiece is sort of like nearer towards like where the focal plane is, imagine it's like your light rays can sort of like split out and diverge. Then you have this like large beam of light coming out right here. But if our exit pupil, let me, I kind of forgot what I was like thinking when I was thinking this. Wait. Alright, this part. Exit pupil is not the same thing as your apparent field of view, right? Because your apparent field of view tells you like the angle that your light is like coming in from like a certain angle, right? And it tells you the maximum angle that light is coming in towards it. But exit pupil sort of tells you how wide this whole beam of light is as it comes out, right? And the two is not related in this sense because you can have short focal length with like this large beam of light over here. Or you have a long focal length with a smaller exit pupil, but your light is sort of squeezed to this point, right? So the reason for that is because this is something that happens with the OTA itself, right? This is like IP side of things. Over here, you have the OTA squeezing light into this specific point, right? So if the OTA has sort of like a short focal length, it's squeezing light at a very steep angle. So that means your light is going to be diverging away from the focal plane at this like very long wide angle, right? So when your light is diverging at a wide angle away from the focal plane, and it hits your eyepiece, then it ends up getting converted into this like gigantic like thick cylinder of light. So the image overall like brighter. Versus if you have a telescope with sort of like a narrow, like with a longer focal length, that means all your light is coming in at a super shallow angle. It hits the focal plane, then it diverges at this shallow angle, right? So the size of your cone is not gonna like sort of like spread out that much. So when it hits the eyepiece, it ends up being converted into this like small, narrow, like cylinder of light, right? So it's for this reason that when you have long focal length telescope, that increases the magnification and that reduces the size of the exit pupil. This is my view of the thing. And again, like when I said just now, this cylinder of light is sort of like finite light. It doesn't start infinity because this is exactly sort of like edge that's like defined by aperture. So aperture sort of defines like just how big this like beam of light can be. And this in turn also like determines your exact exit pupil size. So another concept that you might have heard is the idea of eye reach, right? So let's say like your scope and rifle. You want a certain distance. So when you have a recoil, the scope won't like smash in the eye. In astronomy, for telescopes, we usually have the same thing, right? So there's an optimal distance that you have to put your eye to the eyepiece in order to get a very nice and quick image, right? But the reason is obviously not because of a recoil or anything like that. Yeah. So this diagram sort of tells you what the concept of eye reach is, right? So when you have a whole bunch of like parallel rays that are coming out from the eyepiece lens, and they're all converging into a single exit pupil, the distance of the exit pupil from the eyepiece is exactly what the eye reach is, right? And you want to be putting like your eye right here, because when you put your eye right here, right, your pupil size will be roughly the same as your exit pupil. And right here you can get light from like the red dot and blue dot, so you can see the whole field of view. But let's say you move your eye all the way right here. That means all the light coming in from the edge of the eyepiece will be lost. And they won't like converge fast enough to enter your pupils and like fall in the retina and everything, right? So effectively, that means that when you move your eye too near towards the eyepiece, the edge of the field of view will sort of like disappear, right? So you have negative image, right? The same thing happens when you move your eye sort of like further out, right? So your light rays coming in from the edge, it has to diverge before it enters the eyepiece. So effectively, when you sort of like look through your eyepiece, this is what you get, right? So at this point, at a distance equal to eye reach, the image you see is at the max FOV and also the max brightness, right? But if you move towards the back, then you can sort of see like this, the size of the image being narrower because the light coming at the edges are like getting lost, right? And they're not entering the eye. Same thing happens when you move like too close, then you sort of like see this like fuzzy edge, and then all the details on the edge are like disappearing. So this is the main thing. so damn bloody hard to like take a photo with like phone camera, right? So because you have to make sure that the lens of the camera fits exactly where this virtual executor is, right? So this is literally a point in space that's like floating above the eyepiece right here, and then you can make sure that when you take out your phone, you put this thing is in the line exactly across the spot right here. And the usual, if your angle is slightly off here and there, your executor will basically at this weird angle to it, right? So that means that your image will be lopsided, or you have like this like vertical shadow, right? Because you're seeing like light coming from some parts of the image, but it's not coming from the other parts of the image. So when you have a shorter eyepiece, naturally you tend to have a shorter eye width, right? Because as I said earlier, when you have an eyepiece of a shorter focal length, it's more strongly converging, right? So all your light rays coming in, you get bent more at a sharper angle. So on one side of the eyepiece, your light diverges and it gets bent at a sharper angle, right? Because it needs to accommodate the shorter focal length. But the same thing happens when a light sort of exits on the other side. It also gets like bent towards the executor at a very steep angle. So for that reason, when you have eyepiece with a shorter when you have eyepiece with a shorter focal length, the eye really sort of decreases, right? So that's a disadvantage that you immediately notice when you want to switch to, let's say, a 4mm eyepiece for like 10 viewing, right? Just want to get 200 times magnification. Then you basically have to like take up your glasses with your eyeball over here. It's like very difficult to get a nice, like comfortable image, right? So this is something that's inherent to like the focal length of eyepiece, and it's not something that really change. In practice, you may use something like a Barlow lens. So you increase the magnification without changing the focal length of the eyepiece, right? So you have your effective between the focal length of the telescope, and without really changing how steeply your eyepiece of like focuses the image. So you can still like keep the same eye width and like have like a more comfortable looking appearance. Wait, why did I have this slide? Okay, never mind, I think this slide is lost. Okay, so another concept we want to bring in is the idea of true hypertrophy, right? So for eyepiece, it has an apparent field of view, which is defined by how steeply it basically focuses your light and causes it to converge to an executor. So the true field of view is basically your apparent field of view divided by the magnification, which sort of like makes sense, right? If you can see 50 degrees here in your eyepiece, and you're magnifying your image by let's say like 10 times, then logically what your telescope really is seeing is sort of like 5 degrees worth of like images in the sky, right? So right. So apparently, but the unfortunate thing is that for most eyepieces, they don't have the apparent field of view by self-understand here on the barrel or anything, right? So usually you have to go to like, let's say like the manufacturer's website and go look up a spec sheet or whatever. And then they will usually have like their apparent field of view sort of like you can do in a spreadsheet somewhere. Right. So if you want to do something like let's say like calculate a true field of view, and this is important when you want to say like you want to calculate how fast is a star drifting across the field of view, right? And you use that sort of calculate calculate star magic alignment, stuff like that. Okay, let's not go too far into that, but yeah, if you want to calculate true field of view, then sort of need to like bring out the manufacturer's spec sheet. But a good rule of thumb is that for most of the eyepieces we use, which are like cheaper, more economical options, which are this kind of like proper eyepieces, their field of view is quite standard, like it's around 50 degrees. So you can use that as like a rough gauge to like just how wide is the image you are seeing with the telescope. So all the while I've been like showing you ray diagrams with the light coming in from one side and like converging to the other side, like your eyepiece sort of parallel to it and everything. While in real telescopes, your light rays sort of like bend all at one way. But the main principle over here is like exactly the same, right? So for a refractor, it's obvious enough, right? You have light rays coming in, it's converging here, and this is the focal point. A lot of the times there are things called star diagonals that sort of like fix the image so that you can see from this angle or this angle. But this doesn't really change like everything we discussed, right? Because this is a flat mirror. So you can see like all your light rays here are just being like reflected towards this side. So you can imagine it being like reflected back towards this angle, then everything I said will apply so far. Same thing with mirrors actually, right? So mirrors have light rays coming in, is being reflected towards this side. But what everything I said just now also applies if you sort of like imagine your light rays being like flipped towards this side. Then it's two points are separated by this distance, and you have a point in the middle that's equidistant in the blue sky, when you transform the image, this relation is equal, right? So you have a point that's like halfway in between. But in reality, you may have like what's known as like geometric distortions, right? So your point sort of like shifted here or shifted there. So basically, it's like you dump the image in Photoshop and then you just like check all the points. So the reality is that we have limitations in the kind of like possible lens and mirror combinations that we can put together to sort of like to feel what we want to get out of to redo this thing. The second thing is more like limitation that's caused by like physics, right? Because all the while we are assuming that light comes in the cell of color rays and then it sort of like reflect and like refract through all that elements of gravity. But the reality is that light has like a wave nature, and that is obviously like phenomenon known as like diffraction and dispersion, and this causes a lot of like imperfections in the optical system. So now I'll be talking a bit about like aberrations and things, right? So firstly, you get some kinds of like optical aberrations due to the geometry of your optics and everything, right? So the setback of reality is that no single like simple kind of like lens or mirror can do the job perfectly. And by the job, I mean like taking this cell like parallel light rays and turning it to a single image on the focal plane, right? So the thing is that when we make lens, they are usually spherical in shape because it's usually easier to blind lens that have like sort of like this spherical surface and like curvature to it. Anything that sort of like deviates from being a sphere becomes very, very devilishly like difficult to manufacture. And technically you can do it now, but it's going to be super, super expensive. Right? So typically what telescope manufacturers do is that they use sort of like groups of lens and combine them together like to sort of like get like to sort of like compensate for all the errors in the tool, right? So this diagram is sort of an example of like the kind of things that don't really do when they like try to like design telescope optics, right? So you basically have optics over here. This tells you like the different wavelengths of light and then where are they converging of both the same and everything, right? So they just do stuff like this to sort of optimize the design. And it can get really complicated, as you can see. For mirrors, typically for mirrors it's a lot easier to manufacture a different range of shapes, right? So you can have like spherical mirrors, you can have mirrors that are parabolas or ellipses or hyperbolas and everything. But they're usually still based on like very simple sort of like geometric kind of like designs, right? And the thing is that all of the designs you sort of like have to compromise in one way or another. And usually when you have a sort of better design to correct for more of the errors, they're usually more expensive. So it's a reality of capitalist economy. So because of that, here are some of the common aberrations that you need, right? So those are the aberrations. You typically want to use these aberrations because you want the cheap stuff, right? So cheap stuff necessarily encounter some of the issues, right? So for spherical aberration, that's something you need when you have a spherical optics. Chromatic aberrations when you have parabolic mirrors or like lens that are meant to mimic what a parabolic mirror is. And lastly, you have something like called field curvature, which is quite a difficult problem to address even for like expensive telescope systems, right? So naturally your focal plane will curve and you sort of like need to compensate for that in one way or another. So let's talk about parabolic reflectors, right? I don't know how familiar you are with the idea of parabolic reflector, but you know your car headlamps have a reflector in it, right? And then you have a lamp in the center, which is located exactly where this focus point is. And all your light from this lamp sort of like spreads out, hits the mirror, and it exits your headlamp as sort of like lofty, at a lofty parallel angle, right? And this exactly works in reverse. You have a bunch of like light rays coming in and striking a mirror. It will all nicely and perfectly focus at this very single point, right here, called the focal point, right? So this seems all nice and good, right? This is like sort of has good geometry that does perfectly what we want, right? We want to take a cell parallel light rays and merge it exactly at this single point right here. But the reality is that the parabolic shape only does this for light rays that are coming in at this like parallel angle to the optical axis, right? So if a set of light rays is coming in at a slightly different angle, then you sort of have this sort of spread out effect, right? So effectively, image plane, what you see is sort of like a focus point, and then you have light rays being spread out over a concentric circle that's being offset, and they sort of like overlap each other. So this creates what's known as like a common tail effect, right? So this is what's known as chromatic aberration. And you know this is an issue because when you see, because like in astronomy, you have light rays coming in at like slightly different angles, right? And that's necessary in order to like sort of form an image over like a So effectively, when you take an image of like the night sky, this is the kind of image you get with a parabolic reflector. So all your stars towards the center will be like nice and round and quite focused. But if you look all the way towards the edge of your view, you will see coma. So this is chromatic aberration, right? You can see this bright dot over here, then you can sort of like this halo effect. And then basically all of the common tails are facing out from the center of the axis. And it gets more severe as you move from here to here, 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 here. Right. So but you can sort of counteract this by having a spherical mirror, right? So unlike a parabolic mirror, the shape of a parabola sort of like changes depending on which angle you're looking at it, right? But for sphere, this matter you can just rotate it everywhere. It's all doing the same shape, no matter what angle you're coming in at, right? So another good thing about spherical mirrors is that they're also cheap and like easy to brush, right? And for sphere, you can say that it's almost parabolic if you like use curvature and everything. But spherical mirrors, they're not parabola, so they create something that's known as spherical aberration. So what happens in spherical aberration is that there are some light rays that are focused exactly at the center. But there are light rays coming in from a steeper angle from the sides that are being focused at this huge halo over here. So it's not being focused at this exact same point, right? So the thing is that this error sort of like affects the whole image field like perfectly equally, right? So previously we saw that parabolic reflectors, it really only affects stuff that's like all the way at the edge of field of view. But for spherical aberration, you sort of like get something like this effect, right? So your whole image field is sort of like blurry and stuff. And this is mitigated by making the rays long and everything, right? So the reason the reason that works is because this is roughly what spherical aberration looks like, right? If you notice that all your light rays coming from the very edge of your lens or your mirror or whatever, it sort of like overshoots and like lands in the wrong place, right? But all the light rays coming in from around the center of the mirror, close to the optical axis, roughly converges at where your focal plane is, right? So this set of light rays from this part are known as para-axial rays, right? So they are light rays that are very close to the axis of the optical system. So that means that if you sort of restrict the aperture to this size, then that means that all your light rays that are within this range of angles will sort of be quite focused at this point, right? So this is one reason why you can sort of still use like spheres as mirrors, right? Because if you have a small enough aperture relative to the curvature of the mirror, that results in longer focal ratio, right? So your longer focal ratio sort of like reduce the impact of spherical aberration. So the last problem that I mentioned is the issue of field curvature, right? So previously I was just idealizing and saying that the focal plane is flat and you have the image form on this flat focal plane. But the reality is that your focal plane is actually curved, right? And this is an effect that's more pronounced on like shorter telescopes. So for shorter telescopes, because your light is like sort of converging more strongly, then your focal plane sort of becomes more and more short. I can't really give like a very brief explanation to like why this occurs, but this is quite a big problem. But usually this is something that affects photography more than like visual looking, right? So because your human eye can sort of like compensate for this curved image plane at some point, right? Because your curved image plane has sort of like a focus at a different point. So for example, okay, let me clarify the focal plane idea, right? So because your focal plane is curved, when you set your eyepiece at a focal length at this point, that means that all your light rays coming from the center of the field of view will be focused, right? But all the stuff coming in from the edge will not be in focus. But if you move your eyepiece closer to this side, like where the green line is, then all the light rays coming in from the edge will be nice and focused. All the light rays coming in from the center will be out of focus. Yeah, likewise. But what your eye can sort of do that, your eye can sort of like stretch and like deform the lens that's covering like your eye, like the cornea. You can deform it to some extent that you can accommodate a range of like focus. So your eye sort of like can actually compensate for it. And oftentimes if the field curvature is not too bad, your eye can sort of compensate it, but camera sensors can't do that kind of thing, right? Because camera sensors don't have muscles that just run the lens in front of it. So typically we mitigate this in terms of those kind of expensive gigantic observatories. We use like curved CCD sensors, and they design it in a way that's such that the curvature of the CCD matches exactly the curvature of the focal plane, right? And this is like quite an important you look at a lot of different stuff, a lot of different objects in the sky at once, and you want to do it with a lot, with high precision. So that means that we need to like, be able to mitigate this like field curvature quite clearly. So here's an example of like what field curvature looks like. The thing is that it looks almost like chroma, right? Because you have like stars being perfectly in focus to the center, but if you move out to the edge, you can see like the stars being like defocused and different and everything. But you can sort of differentiate from chroma because if you defocus it a bit, you change the focus, then stars to the edge will be focused, like stars in the center will not be focused. So what I covered before is assuming that light are sent parallel rays coming in, and you are doing all funny things with your lens and everything. But light sort of imposes like even more fundamental limit to your optics, right? Because what light really is like it's a wave, right? So that means that it undergoes what's known as diffraction. So when light passes through like this obstruction or aperture, it sort of spreads out and bends in this like circular fashion. And light also undergoes something called dispersion, right? So you have light, because different frequencies of light sort of travel in your glass or in water or anything at slightly different speeds, then you solve this like dispersion effect, right? So this is the famous like yes. Yeah, but the classic example is the kind of optics we learn in like I don't know, secondary school or DC, they say like Newton, he made this prism right, and he showed a beam of white light to it and sort of splits into rainbow. So this is really dispersion in action. So because of dispersion, you have this effect called chromatic aberration. So the refractive index of glass depends on like the frequency of light, right? So what color the light is. So that means that for different colors of light, the actual point that your light focuses for any given lens is sort of like slightly different from different wavelengths, right? So there are actually two kinds of like chromatic aberration. So first is that the point where it focuses is slightly at a different distance away from objects. Secondly, as you move far away from the field, you have sort of like this splitting effect, right, where the point at which all the light rays coming in from a specific point in the sky gets sent to different points, right? So effectively, when you have longitudinal chromatic aberration, what you have is sort of like all your, okay, in this case, all your green wavelengths are perfectly in focus, all your blue wavelength and red wavelength is slightly unfocused, right? So it sort of like spreads out and gets larger. So this results in what's known as purple fringing. So that means that when you look at a picture of the moon right in the center, you sort of like see this like weird purple halo like spreading out right around it. So that's really chromatic aberration of like this kind, because your blue wavelengths and red wavelengths are sort of like mixing together, like giving you this purple halo. But if you look at stuff that's like on the edge of a field of view, that means the lateral chromatic aberration means that you have the same image, it's nicely focused, but then it's like sort of like shifted laterally, right? So you have this like triple image of like different colors that being spread on this direction. So here's just an example of like the color changing and induced contrast effects, right? So this is something more closer to the longitudinal kind of chromatic aberration. Okay, not exactly, there's still a bit of the red and blue split over here. But the red and blue split can get quite obvious and ugly, like let's say it is like image of Jupiter. So this is the kind of effect that you usually get with refracted telescopes that only have like two lens elements.
In fact, for lateral aberrations,
yes, it's more complex lens designs. I don't know if you heard of like optical telescope, but basically you just insert more lens to focus different wavelengths of light at the same point to compensate. But your telescope will be even more expensive to pay for quality. Okay, the second effect is really because of diffraction. Right? So diffraction means that when you have a set of parallel light rays coming into your aperture, and when you try to focus at a point, the pixel actually becomes different light. So what you really get is sort of this interference pattern that follows the shape of the aperture. So if the aperture of a telescope is round, then you sort of have this circular interference pattern, and this is also known as the Airy. Right? So this is particularly prominent around point sources like stars, right? That are small and they are limited by diffraction. But let's say you have something like the moon, the lunar surface, then it's really not that obvious, right? So it's kind of down. So the thing about diffraction is that if the size of the telescope is smaller, you have this greater diffraction effect. Right? But if the telescope is larger, then the size of this like interference pattern is sort of like reduced to like shrunk to smaller size. So you can easily see like how this means that aperture is related to how what we mean by resolution is that when you have 2 point sources, they sort of have this interference pattern on them, right? We say that you can distinguish them if the interference pattern is at this distance, right? So we have this local minima right here, and they sort of like overlap at this point where we can sort of still see like it's sort of like splitting this area. But if they get close, the 2 bright spots in the center sort of start merging together, and it sort of like becomes sort of elongated block. And you can't really tell whether it's 2 stars or whether it's just that your optics are bad or whatever, or maybe you're like magnetism or something. So overall, the takeaway from this, a larger aperture, you have a reduced diffraction effect, and that means that you can go with bringing these 2 points like closer together before they start merging. So because of that, larger aperture means higher resolution. And diffraction is not limited to just like circular apertures, right? So diffraction also causes what's known as diffraction spikes around stars, right? So that's why in some photographs of the star fields and whatever, you do see like the stars having this sort of pulse on them, right? So usually you have that because they either added it in artificially because the image looks nice, or because they're using a telescope with those kind of spider wings on it. So usually that's why you get with like Newtonian telescopes. So because Newtonian telescopes have this like secondary mirror in front, then it's held in place by these like spikes coming out, right?
So like the GWST.
Yeah, the GWST has like it's a pretty famous example of this. Yeah, exactly. This diffraction pattern. Very characteristic of GWST. But actually the GWST's diffraction pattern is a lot more complicated than that. Right? So technically the 6-star pattern comes from the optical image, but if you add in all the columns and everything, it becomes something like a lot more complicated. But the thing is that it doesn't hurt astronomers that much, right? Because for them, they know that in theory, you have a single perfect point source of light coming into your aperture, and you know that it produces this kind of like shape, right? And they can describe this mathematically using like what's known as the Chorin square function. So that means that they can sort of like use this. They can take the image, they can take this pattern, they use it to reverse engineer like what the image ideally should look like without this interference effect from the telescope itself. So all the while I've been talking about how diffraction limits the resolution of the telescope, but in practice, most of the time you're just going to start fighting against the atmosphere, right? So this is what's known as like astronomical ceiling. So the issue is that because you have like turbulence in the upper atmosphere, you have like all the turbulent eddies that are like swimming around. That means the density of air sort of like changes at like certain points versus other points, right? So that means the refractive index of air sort of like changes, and that means that when the light passes through this like turbulent layer, it sort of like gets bent here and there in this like really part through the atmosphere, right? So this results in like the distortion of like light coming from a point source. So your point source is no longer a single point source in the sky, but it's sort of like that smeared out into this like more like this whatever. So the thing about astronomical ceiling, because it's dependent on the atmosphere, it's very variable, right? So it depends on the local climate conditions. So basically, you at a different part of the globe, you have slightly different astronomical ceiling. And throughout the course of a day or throughout the course of a season, you might have different conditions and it might influence like how stable the atmosphere is. So it becomes like very variable thing. So in fact, like astronomers, some sites have sort of have forecast systems for astronomical ceiling, right? So they'll tell you how good is the ceiling on that night, or how bad the ceiling is at night, and like how clear can you expect to see objects, right? So another thing is that astronomical ceiling, the effects are amplified if you're looking at the stars near the horizon, right? So the classic example is that if you're looking at the sunset, then you can see that the disk of the sun is like warming and stuff, right? Because you're looking through a super thick layer of atmosphere if you're looking through the horizon. So that means that the effects of atmospheric turbulence are super profound. So that means that you have very, very big like distortions like that, like when you look at the sunset. So overall, the effect is that you have to increase aperture, you have to increase resolution. But paradoxically, when you have a bigger telescope aperture, that also like makes the effect of seeing more like severe on the telescope, right? So this diagram sort of like roughly illustrates the idea. If you have, let's say like this small telescope aperture, in reality it's only collecting light from this narrow cone that's like passing through the atmosphere. And if your atmosphere has this level of distortion, if you're sampling light coming in from this like narrow like diameter, right, that means that the variations technically they tend not to be so big, right? So if you take all the light coming from here and you sort of accumulate it, you won't get so much like distortions in your light. As compared to, let's say, if you have a large aperture, you're collecting light from this large area in the sky, right? And that means that you're sort of capturing more of this like disturbance called astronomical scene. So that means that your larger telescopes are more sensitive to like what's known as wavefront errors caused by atmospheric turbulence, right? So there is sort of a trade-off, as you can see here, right? Because resolution increases with aperture, but astronomical scene increases with aperture as well. So at some point you can find an optimum point after that's all changes on a daily basis. Yeah, but the thing is that for astronomical scene, you can, as you increase the aperture, the effect gets worse, but it stops at a certain point. Because at a certain point, you're sampling like just so much of the distorted wavefront already, is that if you're increasing the size, you're not sort of like seeing more errors, right? So basically, you have that when, let's say, like, if your wavefront is sort of oscillating at this size, and you don't have oscillations more than like this size, then that means that if you increase the telescope beyond that size, you won't get any errors. Right? Like, try to illustrate this. You get a rough idea, right? If there's an upper limit to how warm your atmosphere can be, then increasing the aperture beyond that size won't introduce more warmth in the image. Right? So that means that your telescope can be in like sort of this stage, right? Right. So the first thing is that if the telescope is diffraction limited, so it's not the atmosphere that's imposing the upper limit on how sharp images move, then it's the diffraction limit. Then you have to calculate the resolution of the telescope using the traditional methods, right? We use the Rayleigh criterion, and you calculate your telescope aperture deviation and everything. But if your telescope is what's known as seeing limited, then the resolution they can reach has nothing to do with the telescope at all. In fact, it's completely dependent on the atmospheric turbulence, right? So the atmosphere creates what's known as a seeing disk, and only thing you can see in I took this from some research paper, so they're basically doing like simulations of like what a turbulent atmosphere does to like passing through, right? So for some conditions, you can see that like the seeing disk is like this size, others this size. So it's this size of the disk that sort of like determines how sharp the image can be, right? So you can sort of imagine this as like a kind of artificial point square function, if that word makes any sense to you at all. Right. But despite this, we still have large observatories, right? Because twofold, we still want the benefit of large apertures. We want to be able to collect more light, right? So in order to mitigate this, we have like techniques known as like lucky imaging or adaptive optics. Usually what observations do is that they use adaptive optics, right? So they shoot a laser in the atmosphere, and then they use the reflected light from the laser to sort of like know what's happening in the atmosphere. So they know like how is the light being bent and emitted. So they sort of get the point square function of the atmosphere. Then they literally distort the shape of the telescope mirror to sort of compensate for it. So that's what adaptive optics is. But for the rest of us without access to a gigantic observatory, we have to make do with the atmosphere. So usually we have a rule for thumb for what's the best like amount of computation you can use effectively with a telescope, right? So if your telescope is diffraction limited, a good rule of thumb is that you can't use more than 2 times the aperture size in millimeters, right? So let's say if you have a 70mm refractor, it gives you a maximum magnification of around 140 times. For my telescope right here, this is 125mm by diameter telescope, so that gives me about 250 times highest using magnification, which is like quite good already, because usually when the telescope is limited, you want to keep it below like 50 times of magnification, right? So some good nights you may be able to hit 300 times, more than 300 times, but then usually not beyond 300 times, right? Because like beyond that, all you're seeing is just like more effect as a result of the atmosphere. And in any case, most of the things you want to see in the night sky don't require magnifications as high as 200 times, right? Usually the only things that benefit from such a high magnification is that when you want to look at the surface details like craters on the moon or whatever, or you want to look at the details of like the planets. numbers that we care about is aperture and the focal length, and of course how expensive this is, right? Because there are very how can we use equipment. And for eyepieces, the numbers will be known, focal length, apparent field of view, and the cost of eyepiece, because the eyepieces also can cost as much as the physical design, so we're able to afford it. So, on the field, you also need some quick formulae to solve the calculations. Using stuff like, let's say, how much of the magnifying things, your true field of view versus your apparent field of view. You want to know like what's the focal ratio of the telescope. Or let's say if your telescope gives you the focal ratio and aperture, but it doesn't give you the focal length, then you can sort of like calculate this by multiplying the focal ratio with the aperture. Then you want to know things about like how bright image will be, then you calculate it using the formula. And rule of thumb, your maximum useful magnification is roughly 2 times the aperture of the telescope, or roughly 250 times, which is the limit caused by atmosphere. So this is just about summary of the practical stuff we need, and then this is the end of the class. Right, so as usual, I'll have like a quiz after this, and then after that, hopefully you'll be able to get stargazing done. I'm not sure how bad the weather is, right? So just let me check.
It's quite cloudy.
Ah, okay. So now I can explain.